So as we start our class today, let me just repeat once more about what we mean by this hysteresis curve, the inherent meaning of this hysteresis curve. Here in this hysteresis curve, actually it is basically, this curve is showing the loss of energy due to hysteresis per unit volume of the material per cycle of magnetization. Okay, and this is basically given by the area of this BH loop, which is integral over the closed contour HdB. So like for example, I've drawn a very rough hysteresis curve, a thinner one. So this basically shows the amount of energy loss in that particular ferromagnetic material, and therefore it helps you to choose a material for any device making, and it plays a very crucial role over there. So drawing a hysteresis curve and finding the area helps us to find out the energy loss, the loss of energy due to hysteresis per unit volume of the material per cycle of magnetization. So this is a very important input before we move over to ferromagnetism, because ferromagnetism is the topic which they have asked us to cover in detail, not paramagnetism and diamagnetism. However, the salient features of all needs to be known, which we have discussed already. Now the point is that in order to learn ferromagnetism, it is important to know paramagnetism, because by now all of you know that above a specific temperature Tc, even a ferromagnetic substance becomes paramagnetic. So basically, therefore, we need to know we need to have some basic idea about the theory of paramagnetism. Okay, so for example, if we start with chi para is equal to C by T, and that is of course equal to M by H, whereas chi ferro is equal to C by T minus theta. This is also chi para, provided T is less than Tc, which is the specific Curie temperature. So if it is more than Tc, then again the same formula, this is the Curie-wise law actually, it becomes paramagnetic, and it applies to a paramagnetic material. A little bit of theory, a little bit of theoretical expression, if you know, you don't have to know the derivation, because a part of this we have already learned, specifically this Langevin function. This is called Langevin theory of paramagnetism, but you don't have it. So basically, the magnetism in a magnetization in a paramagnetic material, it goes as N mu m. Mu m is the magnetic moment times L beta. Okay, where what is N? Well, N is the total number of dipoles within unit volume. Capital N, this N is actually the total number of dipoles within unit volume, and L beta is basically the Langevin function. It goes as cot hyperbolic beta minus 1 by beta, where beta is given by mu m b by kt. Okay, so with this we start with this basic input for magnetization, which one derives for paramagnetic substances. Now, because ferromagnetism is a limiting case of paramagnetism, or rather after a certain limit, a ferromagnetic material becomes paramagnetic. Therefore, we need to know this formula before we talk in details about ferromagnetism. Now, the important thing over here is what happens. This little bit of information we need to know. What happens when mu mb is much greater than kt. Okay, when mu mb is much greater than kt, then, well, we see beta is much greater than 1, and L beta, when beta is much greater than 1, suppose we take beta going to infinity, then L beta goes to 1, and we get the saturation magnetization in that case, which is Ms, and that is given by N mu m. So N mu m equal to Ms. Ms is your saturation magnetization. This is saturation magnetization, and when mu m beta is much less than kT, then what happens? Then actually m goes as N mu m beta by 3. Okay, N mu m beta by 3. So if you just put the value of beta, what you get over here is N mu m square b by 3 kt. Okay, so this happens when the value of when beta is much less than 1, and then the Langevin function gets modified in this manner. Just if we draw the graph, if we just draw the graph, then the graph of say L beta, if we plot L beta versus beta, if we plot it like this, then you will see that for low this graph actually will go like this. This value is actually equal to 1. Okay, so for high values of beta, the saturation occurs at value close to 1, so it's nearly close to 1, and for low values here, well, this is equal to beta by 3. So this is what, if you remember the graph, you will remember the expression. Okay, now so the Curie constant C, if you look into the Curie constant, the Curie constant C is equal to N mu naught, okay, mu m square by 3k. Okay, so here what is it that we observe? We observe that m is proportional to b by t. What does it imply? This implies that the increasing b tends to align the magnetic moments in the material so that m increases, whereas increasing t tends to disorient the moments, as a result of which m decreases. So m cannot increase without limit, as t tends to 0 and b tends to a large value. It can at best approach the value ms, which we saw just now, corresponding to the complete alignment of all n dipoles contained in a unit volume of the specimen. So in order to achieve 99.5% or 99.9% saturation, it is necessary to use magnetic fields as high as of the order of say 5 Weber per meter square, that is 50 kilo Gauss, and temperatures as low as 1.3 Kelvin, that means very close to 0 Kelvin. So this law, which is Curie law, it is actually valid when B by T does not become too large. Okay, so with this little introduction to paramagnetic theory, the theory of paramagnetism, Langevin's theory, let us proceed to our knowledge of our understanding of ferromagnetism.